In this video, we're going to cover the basics of chromatography and how it is used in thin layer chromatography, column chromatography, and gas chromatography, including GCMS. We're going to start off by recapping the basics of chromatography, which you'll have covered in GCSE. Chromatography is used to separate the different components in a mixture. Depending on the kind of chromatography you do, you can then collect the different components and do further analysis on them. Chromatography works by separating compounds based on two phases. The first of these is the mobile phase, and this is where the molecules can move through that particular phase. And the mobile phase is either a liquid or a gas. You also have the stationary phase. And this is where molecules can't move through it. It's either a solid or a liquid on a solid support. The idea behind how chromatography works is that the mobile phase moves through or across the stationary phase. Your mixture will typically be dissolved in or carried by the mobile phase as it moves through the stationary phase, and the distance moved by a particular component within that mixture will depend on two different things. How soluble that mixture is in the mobile phase, and how strongly that component is retained by the stationary phase, so how long it spends adsorbed onto the surface of the stationary phase. Each different component will have a different solubility in the mobile phase, a different retention by the stationary phase, so each component will move through chromatography at a different rate. Therefore, it'll be collected or separated at a different time, and we can then determine what these different substances are by looking at their retention factors, which we'll cover later, or by collecting them at different points and doing further analysis on them. We're going to start off by looking at thin layer chromatography, sometimes abbreviated to TLC. TLC uses a liquid solvent, usually ethanol, and this is the mobile phase, and this is done on a silica plate. It's silica usually on a glass or plastic or aluminum plate. This is different from what you'll have done in GCSE, where you'll have done paper chromatography. Proper TLC is done on a silica plate instead. And this is your stationary phase. This is a required practical, which is covered separately in the required practical video, but the general process for how you'd separate a mixture using TLC is that you draw a line in pencil near the bottom of the plate and put a small amount of your mixture on the line. If you were comparing multiple different mixtures, you could have multiple different spots along the bottom, just making sure you'd separated them out. You'd wait for your spots to dry. You'd then place your plate in a beaker with a small volume of the solvent, making sure the solvent level is below the baseline so it doesn't dissolve your samples away into the solution at the bottom. Given that we might use ethanol or another volatile solvent, we typically put a watch glass on top of the beaker the TLC plate is in to stop the solvent evaporating away. The solvent will then move slowly up the plate, and as it moves, it'll carry your substance with it, and as we've just discussed, depending on how well it dissolves in the mobile phase or how strongly it adsorbs to the stationary phase, the components in the mixture will separate out at different rates. Once the solvent has reached the top, you remove the TLC plate from the beaker and mark the solvent front so you can then calculate the RF later on. You'd then leave your TLC plate to dry, and then you'll be able to do the analysis on it. RF values allow us to compare the position of a spot on a TLC plate across different TLC plates of different sizes. So for example, if you did a plate of length 5 centimeters and one of length 10 centimeters, the spot would obviously move up a different amount on each. To calculate the RF value, you do the distance moved by the spot divided by the distance moved by the solvent. You take both measurements from the baseline. So for example, let's say that the spot has moved up 50 millimeters and the solvent has moved up 75 millimeters. Our RF calculation would be 50 divided by 75, giving us an RF value of 0.66. We're now going to look at a different kind of chromatography called column chromatography. This is used to purify and collect different organic products. So we're not going to calculate an RF value in the same way that we've done with TLC. This is used if we've done an organic chemical reaction and we've got a series of products in a mixture. This allows us to separate those products out and collect each one separately. So in column chromatography, we have a glass column which is packed with an absorbent solid coated in water, and this forms something called a slurry. For example, we might use silica powder soaked in water, and that is the white slurry you can see inside the bottom bit of the column. This is our stationary phase. We then add a solvent to the top of the column, and we can see this here, and this runs down through the stationary phase and can come out of the bottom here. This is essentially like a big burette, so there is a tap at the bottom so you can drain the solvent off. And this is the mobile phase. We're now going to look at how column chromatography works. We can imagine that this is our column with our slurry inside, so these white circles represent the stationary phase. We would add our mixture to the top of the column, so in this case our mixture contains two chemicals, the blue and the red. We then add the solvent, the mobile phase, on top of the mixture, and this will cause the mixture to move down the column. The components, the blue and the red, will separate out inside of the column based on their solubility in the mobile phase and how strongly they are adsorbed onto the stationary phase. They'll then be collected in a beaker at the bottom of the column. So for example, as the solvent moves down the column, our two components will start to separate at slightly different rates. As we can see, the red is probably more strongly adsorbed to the stationary phase, and the blue is more soluble in the mobile phase, so the blue is travelling down the column quicker than the red is. This process will keep on happening, and the components will become further separated out until the blue is being collected at the bottom, and the red will eventually make its way down and also be collected, but separately from the blue. We're now going to look at gas chromatography. Gas chromatography is used to separate a mixture of volatile liquids. A volatile liquid is one which can quite easily turn into a gas. They typically have very low boiling points. As part of this process, the volatile liquids are separated out and then identified separately. A gas chromatography machine consists of a long coil of a solid or a solid coated with a liquid. This is your stationary phase. Your mixture is inserted and mixed with an unreactive carrier gas, which is then passed through the solid or solid coated by liquid. That's the mobile phase. As the different components pass through the stationary phase, they are recorded by a detector. That will produce a gas chromatogram, which records the amount of the substance and the time it reached the detector. So that could give you a result of something a bit like this. We could see as the time progressed, you'd have your units of time along the bottom, so it could be every 2 minutes, for example. It would let you know a different component was detected. As each component will travel at a different rate through the column, therefore we can work out how many different components we must have had. So if this was a chromatogram for a mixture, it would consist of 5 different substances. You can work out the area under the peak to determine the relative amount of it which is in the mixture. So as well as identifying how many different components are in a mixture, gas chromatography can also tell you the relative amount of those different components. You can also use a combination of gas chromatography and mass spectrometry called GCMS. This is where your gas chromatography machine is connected directly to a mass spec machine. It works exactly like the example we've just looked at. So the gas chromatography machine will separate all the components in a mixture, but those components are then fed straight into the mass spec machine, which can then identify the MZ of each component. So as well as working out how many components they are and their relative amounts, we can then get an MR of each of those components. And computers can then compare those results to a database to identify the different components and the different compounds within that mixture. This is typically used by police in evidence labs when they're calculating alcohol levels in blood or urine, because we can identify the relative amounts of those chemicals as well as them just being present. So it wouldn't just tell us that alcohol is present in blood or urine, it can give us the relative concentrations as well, which could be used, for example, when looking at drink drive limits or other forensic investigations.